Good evening. Let's turn in the quizzes. Moving right along, we discuss sequences. This is a power series, it's an infinite sum. The starting value can be anything. The two most common, 0 and 1. If you only take the first n values, sum those up. That's called the nth partial sum, S sub n. Right, and then S is the sequence of all of your partial sums. A sub n is just some general term. But how do you sum up an infinite sum? Right, so you have an infinite number of values. How do you actually calculate that sum? Oops, okay, so I don't actually want to call this S. So if you take the sequence of partial sums, if that converges to some value, call it big S, then we say that the series itself converges to that value, and we'll write the sum equals S. And there were weird occurrences with infinite sums. One of the weirdest which You'll react to the video on it next week. Because if you look at this sum, so it's just the sum of the natural numbers, sum of the positive integers. What do you think that sum would be? Right, so you just take all the positive integers, sum them up. What do you think that sum would be?
Just be infinity.
Infinity would make sense, wouldn't it?
Yeah.
It's been shown to be negative 112. There are several, I don't want to call them proofs. There's one proof, but there's several ways they get negative 112. The proof that I read uses the Riemann hypothesis, which has yet to be proven. So, for all we know, this result is false. Another strange thing about this result shows up in string theory. Which is the theory that is supposed to weave together quantum field theory and general relativity. Currently two camps. The camp that says that's absolute nonsense, and then the camp that accepts it. I'm in the camp of it being absolute nonsense. But there you have it. That's a very weird result, and you'll watch a number file video on that next week. So I would recommend you have a separate sheet of paper to write down the tests and special series that we look at, because we're going to go over the first two right now. Geometric series. So any series of this form, C times R to the n, where both C and R are non-zero. Converges whenever the absolute value of R is less than 1. R is called your common ratio. The series will diverge if absolute value of R is greater than or equal to 1. And it's shown that when it converges, it'll converge to the value c over 1 minus r. Something important to keep in mind. It is important that it starts at 0. If your geometric series does not start at 0, it will not converge to c over 1 minus r. It converges to something else. It's not too difficult to determine that. Another important property of series. The first finite amount of terms does not affect convergence. So if I have a series that converges, and I take away the first 100 million terms, it still converges. If I have a series that converges, and I add in 100 million terms, it still converges. The sum of two convergent series converges. Product of two convergent series converges. Quotient of two convergent series converges. If you try to add convergent and divergent, it will diverge. Which makes sense. You can't add so you can't do 5 plus 1 over 0. That doesn't make sense. 1 over 0 doesn't converge. It's undefined. Then we have divergence test, or sometimes called the nth term divergence test. So here's what the divergence test says. If your series converges, then the nth term converges to 0. Again, remember, whenever I'm talking about limits in this case, it's always n goes to infinity. I'm just not going to write it. But this is not an if and only if statement. So if you calculate the limit of the nth term and you get 0, it doesn't necessarily mean your series is going to converge. This is just saying that if the series converges, then the limit's guaranteed to be 0. Which means, as the test is actually stated, it's useless. However, we take logic. This statement is known as a conditional statement, if then. There are 3 alternatives to a conditional statement, 3 other ways, or I don't want to say other ways to write it. There's 3 other forms. You have the inverse, the converse, and the contrapositive. Inverse and converse are logically equivalent to each other, meaning they say the same thing. They have the same truth values. The statement and its contrapositive are logically equivalent. which means they're the same. The contrapositive of this test, of this statement, is that if the limit is not 0, then the series diverges. That is the more useful statement. So again, keep in mind, there's a reason why we call this the divergence test. It only tests for divergence. It can never conclude convergence. Right? Because again, if the limit is 0, that doesn't mean your series converges. It could still diverge. So here we have a series. We're asked to examine it for convergence. So just examine and determine whether it converges or diverges. Well, let's write it in summation notation. And this is summation notation. Try and move on. Do you know what that symbol's called?
Sigma? Or F?
Be more specific. There are 2 sigmas.
Oh, is it a Greek sigma? Or?
There are 2 Greek sigmas. Just like there are 2 A's.
Is it the capital one?
It's capital sigma. Right? Your lowercase sigma.
Oh,
Look at that. So we want the general term a sub n, right, which is kind of what we were working on Monday. We're looking for the general term of sequences. So we have 1/5, 1/25, 1 over 125, so on and so forth. So what is the general term? So if I were to ask you for the nth term, what would it be?
N?
Because that's what the general term means. What would the nth term be?
1 over 5 to the power of n?
All in parentheses?
Yeah.
Or like this?
No answer. Yeah, that's what I'm thinking. What is the other option?
1/5 all raised to the nth power.
Oh, no.
They're actually the same.
Yeah, I was wondering if they'd be this. Yeah.
Isn't 1 to the n just 1? So for purposes of this problem, I'm going to write it that way. They're the same thing. Where does n start?
1.
Starts at 1. So at 0, your first term would be 1. Oh, well, that's geometric. Remember, I can eliminate a finite number of terms from the start. It doesn't change how the series behaves. So that's geometric. What's R? One over 5. Absolute value, is that less than 1?
Yes.
This converges.
How do we know R is 1 over 5?
Look at the form of the geometric.
So in this case, C would be just 1?
Yes, C would be 1.
Okay.
Right. What's being raised to the nth power? That's your R.
Yeah.
But if we just write it down like 1 over 5 to the power of n, so like only the denominator to the power of n, then R would be the same.
It would still be the same, but to see it more clearly, you write it in this form. Right, so 1 over 5 to the n is still geometric
But
because
R
it is 1/5 to the n. Right? These are the same. They are the exact same series.
Yeah, but you said that R is something that we're
Right, raised into the nth power.
power. So in this case, it's going to be only 5.
No, it'd be 1/5. Because you're still raising the whole thing to the nth power. 1 is still, you can still raise 1 to the n. Right? You couldn't say R is 5 because that doesn't say 1 over R to the n. Right? It's just R to the n. So this whole thing would have to be raised to the nth power. But since it's 1 to the n, 1 to any power is still 1. So you can just raise it to the nth power and you're done.
How do we determine that C was 1?
What's 1/5 to the n being multiplied by?
I guess 1, yeah.
Right? 1 times anything is itself, so if you don't see anything there, it's an implied 1.
Okay.
And so that converges. Now let's determine what it converges to, even though it's not asking for that. So to start with, n equals 0, n equals 1. That's no good. This to here. I can shift it down. So what I really do is technically replace J. We replace N. With a new variable, let's say. So we're substituting n with j plus 1, which means j now starts at 0, not 1. This is what you're supposed to do. I just use the same variable because it doesn't matter. So I just replace n with n plus 1. Okay, well, I'm still now not in this form. But 1/5 to the n plus 1. If you have a to the n plus 1, how can you rewrite that? Think back to laws of exponents.
Was it maybe a to the n times a?
It's a times a to the n, isn't it?
Yeah.
Now it's in proper form.
Now it will look like c is 1/5.
C is 1/5.
Okay. Interesting.
Right, so by this theorem that says what it converges to, which is derived in the video, C over 1 minus R. It's 1/5 over 4/5, which is what?
Look, it's 1/4.
This sum is a quarter.
Good.
Right, so if you add up all of these infinite number of terms, you'll get a quarter. That's what it's saying. Technically, you don't get, it converges to a quarter. Right, the sum's approaching 1/4. It never actually gets to a quarter because what is infinity? But we just say it equals it because that's what it's converging to. Right, which is where the whole idea of -1/12, the sum doesn't equal -1/12. Because it's an infinite sum. We're being asked to show that this series diverges. Well, let's try divergence test first. Which means we're going to need to write this in general form. So we're going to need the nth term. Write it in summation notation. Denominator is the easiest to start with. So denominators 2, 4, 8, 16.
Squared.
What would be the next one?
32.
32. What would be after that?
64.
So what would the nth term's denominator be?
It would be like 2 to the n.
Now we have to figure out the numerator's term. 1, 3, 7, 15. So what's going to be next?
31.
And after that?
63.
So what's the nth term's numerator going to be?
Numerator plus denominator.
What is it?
Numerator plus denominator of the.
So how did you determine
the formula? So 2 to the power of n plus.
Right, so I do agree there's a 2 to the n.
Minus 1.
Minus 1. Right, how'd you get 31? You took 32 and subtracted 1.
Yeah.
Right. 63, 64 minus 1. So it's the denominator minus 1. N starts at what?
Well, there it starts at 1.
1 to infinity. So the divergence test says if the limit of this term, the nth term, is not 0, the series diverges. What's that limit?
I think it's going to be negative 1.
Three ways to approach this.
Oh no, it looks like, I think it's actually approaching 1.
It's
Yeah.
1. 3 ways to look at it. First way, you have 2 to the n minus 1, you have 2 to the n. They're both exponential functions. It's even nicer is they also have the same base. So it's going to behave as 2 to the n over 2 to the n, which is 1. You could also use L'Hopital's rule on it. Derivative of 2 to the n is what? You know this.
Yeah, I do. It's 2n to the power of n minus 1.
Because it's not a power function, it's an exponential function. And we did cover it in Calc 1.
Is it still 2 to the n?
There's a 2 to the n times something.
Oh, I think I remember talking about it, but it's
I may have mentioned it on the first day as well in this class. It's 2 to the n log 2. So you get 2 to the n log 2 over 2 to the n log 2, which is 1. The limit's 1. Third way is you can just split this into 2 fractions. 2 to the n over 2 to the n is 1. 1 over 2 to the n. So you get 1 minus 1 over 2 to the n. What's the limit of 1 over 2 to the n?
0.
0. So you get 1 minus 0, which is 1. Those are the 3 ways you could tackle it. The important thing, that's not 0. And so the series does diverge. All right, let's look here. 9 minus 12 plus 16 minus 64 over 3 plus 256 over 9 minus so on and so forth. So what would the next term be? You see the pattern.
Starting to see a pattern, but interesting.
Where is it? It's here somewhere. Can't find it. So we're at the next two terms.
I don't know what the next term is, but I could see that the one term after the next one will be 324 over 9, is what my pattern is telling me. It's not.
What they know? Look at the denominators. 3, 9, 27, 81. What do you notice?
Like it's pretty good on the right side, but on the left side, the first three.
Yeah, just ignore that for now.
Just multiply by 3 every time.
So it's a power of 3 each time, right? What about the numerators?
By 4.
The powers of 4. Oh, but you said the first 3 terms? Well, can I write 16? 16 of 1? Isn't 16 a power of 4? Isn't 1 a power of 3? This also fits the pattern. These two don't. But that's okay.
What's the next term after that?
Like 16 something.
So it would be Be 4 to the 7th over 3 to the, no, 4 to the 6th over 3 to the 5th.
But that somehow evaluates a 400 over 9.
Oh, maybe you simplified it.
Yeah, maybe.
Maybe you reduced it, which is possible,
Okay.
which doesn't help us with our pattern recognition. So why don't we just do this? What's 9 minus 12?
-3.
-3 plus a sum. N equals something to infinity. So the question is, where do you want n to start? 2? 0, 1, 2?
Well, would the first term be 0?
You can make it the 0 term.
Okay, because I thought anything to 0 powers.
No, I'm not saying power. I'm just saying 9 would be the n equals 0 term.
Okay.
12 would be the n equal 1 term.
Okay.
This would then be the n equal 2 term in the sum.
Okay.
I don't know why I did parentheses. And then what do we get? It'd just be what? 4 to the n over 3 to the n minus the n minus 2, right? Right, yeah, so I was right. It would be 4 to the 7th over 3 to the 5th. Be the next term. 4 is 2 ahead, not 1 ahead. Three to the n minus 2 would be 3 to the n times 3 to the minus 2, right?
Yeah.
Now the question is, do I want to do that? Because I want this to start at 0, so you know what, I'm not going to do that just yet. Because I'm going to actually get rid of that n minus 2 when I shift this down. So I want my n to start at 0, so I'm shifting n down by 2, which means I have to replace n with n plus 2. That's better. And 4 squared. Ooh. Right now there's a mistake. A very minor mistake.
Where do we get 16 from?
4 to the n plus 2.
Oh, because it would be
Be 4 to the n times 4 squared.
Okay. Yeah, something has to be negative.
I'm going to make one of my terms negative. I'm going to make it -4 to the end.
Yeah.
Well, I could just throw in a -1 to the end. I just have to make sure 2 is positive. Okay, good. Which means 3 be negative, so we're fine. I don't have to worry about adjusting it. Which means that's -4, and that would be -4/3. Right, so whatever this series does, the entire sum's going to do. Right? If this converges, if I subtract 3 from it, it still converges. So the whole sum will converge. If this diverges, subtract 3 from it, it's still divergent, so the original sum will diverge. Right? Which is why the fact that the first 2 or 3 didn't match the pattern doesn't matter. The first 100 million could have not matched the pattern, and it doesn't matter. Right? As long as at some point for every value after it, there's a pattern. That's what matters. Does this series diverge? So we look at this. That's the one we're looking at. Let's do an arrow to signify I'm not doing a negative in front.
Well, isn't it going to vary between positive and negative depending on what the power is?
Sure, but that doesn't matter. Does the series itself converge or diverge?
But for the limit, how can it approach 0 if it's like? I think it doesn't approach 0.
So you think it diverges?
Yeah.
I agree. You don't have to use divergence test though. You can, you don't have to. Isn't that geometric?
But like if it's the CRN, yeah.
C is 16, R is -4/3. Absolute value of -4/3 is what?
Greater than 1.
It's greater than 1, diverges.
Yeah.
Which means our sum diverges. Now we want to evaluate an infinite sum. So start with that. One of the rules of exponents, numerator and denominator has the same power. So can't you just raise the entire fraction to that power?
Yeah.
So what would the original fraction be?
-1/2 to the end.
Oh. It's not geometric. What's R?
1. Or you could say -1.
-1, go with 2.
Yeah, it's -1/2, right?
Oh yeah, R. Yeah. Yeah, 1/2. Yeah.
Absolute value of negative 1/2.
1/2.
Is that less than 1?
Yep.
This converges, so it does have a sum. What does it converge to? C over 1 minus R. What's C?
1.
1 over 1 minus negative 1/2. That's 3/2, right? Sum is 2/3. There's a really cool application of geometric series. So do you remember way back in pre-calc? Actually, it's before pre-calc. Way back in, when do you look at fractions? When you study rationals? 3rd grade?
Something like that.
What does it mean for a number to be rational? You can write it as an integer divided by an integer, right? When would a decimal be rational? Right, so for instance, pi is irrational, right?
Yeah. I guess I think a decimal is rational if it either repeats or it terminates at some point. Maybe.
So there's a finite number of decimal places, so it terminates, or it begins repeating. So that's what?
Rational.
What's the actual fraction?
Oh, 2/3.
That's 2/3, right?
Yeah.
Because that 6 is going to keep repeating forever. So even though the decimal doesn't terminate, it has a pattern. That's rational. What you can do with geometric series is write any infinite repeating decimal as a fraction. You can actually determine what its fraction is. You actually don't need geometric series to do this. I'm also going to show you how we do it algebraically. So look at 0.9 repeating. I'm going to write this as a fraction. And this is an interesting result. First, I'm going to do geometric series. Well, if you look at 0.9 repeating, be 9/10, right? Plus 9 over 100 plus 9 over 1,000, so on and so forth. Write that in summation notation.
Nine over 10 to the power of 10.
What's being raised to the power of n?
Only denominator. Only 10.
Only the 10? And so let's write it that way. Where does n start?
1.
That's almost geometric.
0.
Have to add 1, right, to n, because I'm shifting it down to n equals 0. Which means I'm getting an extra 10th out of that. Right? R is 1/10. Absolute value is less than 1. This converges. It converges to 9/10 over 1 minus 1/10. Point 0.9 repeating is 1.
Yeah.
That is a very interesting result. Whenever you have a 0.9 repeating, you can rewrite it as 1.
That's what the approach is.
So if I give you 4.9 repeating, that's 5. I'll charge you $19.99 repeating. Seems cheaper than $20, but it's really just $20.
Because at some point there's no half a cent.
Right. So that is using series. We can also do this algebraically. Let x be 0.9 repeating. What's 10x?
Okay. Well, 10.
Remember, we don't know that 0.9 repeating is 1 yet.
Okay.
9.9 repeating, right?
Yeah.
Subtracting. Nine 9.9 repeating minus 0.9 repeating is what? 9x is 9, so x has to be 1. These methods are valid for any repeating decimal if I wanted you to put it into fraction form.
Well, it wouldn't work for something like 0.7 repeating, right?
That's what.
It would?
Yeah.
Okay.
Which technique do you want to use?
Oh, I guess we use geometric.
You want to do geometric?
Yeah.
It's going to be an easy fix. So instead of 9, I'm going to use 7. So all become 7s, right?
Yeah.
That 9 becomes a 7. That's 7. That's 7. That's 7. That's 7. This would become 7. This would now be 3, right? It's not right. So that's 10/3, that's not right. 7/3, that can't be right. What happened? Oh, wait a minute. Sorry. That's still 1/10. Okay, that makes more sense. This is 8/10 now.
Well, 1 minus 1/10 would be 9/10, wouldn't it?
You're right. 7/9.
Okay.
And so you can do it no matter what the repeating decimal is. Just depending on what's repeating, it may be a little more complicated.
Okay.
Right, so if it's like 0.123 repeating, for instance, it wouldn't be this simple. But the method itself is still the same.
Okay.
I want to determine whether this converges or diverges. So first, write it in summation notation.
Is that 1 over 1 times 3?
Yes.
Okay.
Right. They're nice enough to actually write it that way instead of 1/3, 1/15, 1/35, 1/63.
I would say, is it maybe 1 over n times n plus 2?
What's the problem with that? If you do n over n plus 2, you're also going to get evens. Or n times n plus 2, you're also going to get evens. Right? For the n equals 2 term, that would be 2 times 4.
Is it maybe something?
So what do you notice about the denominator? Isn't it always the product of consecutive odds?
Yeah.
Those are consecutive odds, aren't they? You could have also done 2n plus 1 and 2n plus 3. Your n would just be different. Your starting n would be different. And then start n at 1. That is not geometric. What is the limit of that term? Should be obvious. Zero.
Yeah, it's getting.
The denominator is increasing.
Yeah, no.
The numerator stays the same. Divergence test fails. And this could either diverge or converge. We don't know. Bummer! Guess it means we're going to have to look at the sequence of partial sums. Because we don't have any other tests right now. Before we do that, let's write this in its partial fraction decomposition. Oh, there's a term you thought you'd never hear again. Oh, it's back. I don't feel like doing algebra. Mathematica can do partial fraction decomposition for you. It's the apart command. Now you just type in the fraction. And I think, no, you don't need that. Oh, you need to do another one of those. I think you can also specify what the variable is, but I don't think it's needed. So if I just do this, it should give me my decomposition. So it's going to be a half over 2n minus 1 minus a half over 2n plus 1. So here's our new sum. I say new. Same sum, different form. What is the nth partial sum? Well, it's going to be 1/2 times the n equals 1 term, which is what? 1 minus 1/3, plus n equals 2 term, 1/3 minus 1/5, plus the n equals 3 term, right? 1/5
Minus a 7.
minus a 7th, so on and so forth, up until the big nth term. 1 over 2n minus 1 minus 1 over 2n plus 1. Dramatic music. Negative 1/3 plus 1/3. Negative 5th plus 1/5. Negative 7th is going to be plus a 7th. Right? You're going to have a minus 1 over 2n minus 1 in the previous one. Plus. Oh, look at that. All of the middle terms cancel out. What are we left with? Our first term, our first and last. This is called telescoping. This is a telescoping series. There's our nth partial sum. Take its limit. What is it?
So 1/2.
It's just 1/2. Series converges to a half.
So if we had tested that and found that the values were getting, like the value that one was minusing was getting larger instead of smaller, does that mean it would diverge?
It depends on what the limit is.
Okay.
Right? Values could be getting larger, but still essentially. But they could be getting larger, but not without bound. Right? So they could be getting larger, but say getting larger to 10. The series would still converge, right? Because your limit wouldn't be infinite.
Oh, okay, so it only diverge.
It'll only diverge if the limit does not exist.
Okay.
The limit of the partial sums.
So
Right, so it completely depends.
okay.
All right, let's look at this series. Does this converge or diverge? So again, write it in summation notation. So what is the summand going to be?
3 to the power of 1 over n. N is 1.
3 to the 1 over n goes from 1 to infinity. There's summation. Well, it's not geometric. The only other test we have right now is divergence test, so let's try that and see what we get. What's that limit?
Zero.
So remember, composite function theorem. N's going to infinity. For infinitely large values of n is 1 over n continuous. Yes, right? It's only discontinuous at 0. Well, we don't care about 0 because we're approaching infinity. Composite function theorem says, I can do this, 3 to the limit of 1 over n. What is the limit of 1 over n? What does that converge to?
0.
It's 3 to the 0, which is what?
1.
Is that 0? Is that 0?
Oh.
Series diverges by the divergence test. And so when you got 0, you were probably just looking at 1 over n.
My logic was like if it's decreasing every next step.
Sure, it's decreasing, but that doesn't mean it's decreasing to 0. Right? In this case, it's decreasing to 1.
All right.
Are there any questions on infinite series? You seriously freaking reset on me again. That's annoying. So write this in summation notation. And keep in mind, they're giving you a starting value of n equals 0. Well, we know it's going to be cosine of something, right? Let's start with that. But now cosine of what?
3 plus 5 multiplied by n. 5 is multiplied by n.
What was it? 3 plus
5, and only 5 is multiplied by n.
5n?
Yeah.
think it might be 3 plus 10 plus 5. Something like that.
Yeah, that looks good. When n is 0, that's 3. When n is 1, that's 3 plus 5, which is 8. N is 2, that's 3 plus 10, which is 13. When n is 3, that's 3 plus 15, which is 18. Ooh, this is a long one, 25. I bet the first 5 is pattern recognition. Yeah, I can guarantee the first 5 is going to be recognizing patterns, not actually determining anything else. All right, so what about here? So let's get started with, again, n starting at 0. It alternates. So I'm going to put a -1. Even terms are negative. So let's do an n plus 1. So now it's what? Divided by 5, 13, 21, 29. That. Here's another cosine. N starts at 0. I'm starting to see a pattern to their questions. They're not making these very challenging. So what is it?
7 plus 9.
Oh, finally, one about properties. Okay. Yep. So this one should be fairly simple. So summation is what's known as linear. Those are the linearity properties. Right. So they tell us that the sum of an is 4, sum of bn is -9. This sum would be -6 times 4 plus -4 times -9. So -6 times 4 is what? -24? What is -4 times -9? 36? -24 plus 36. Same sum, except look. We're now starting at 2. So we took away the n equals 1 term. So it'll be 12 minus whatever that n equals 1 term was. Right? Well, a sub 1 was -5 and b sub 1 was 3. So that first term, -6 times -5 plus -4 times 3. Right? What's -6 times -5? 30? -4 times 3 is -12. What is 30 minus 12? 18. So 12 minus 18. Ah, okay. Evaluating some sums. I think that's what the next 5 are. I'm gonna cheat. This one isn't too difficult to do by hand. Sum command. It was what? 1 plus -1 to the I. And then I went from 1 to 6. Oh. Six. Right. How do we do it in our head? Well, I'll just start with I equals 1. When I equals 1, you get what? 1 plus -1, which is 0. When I equals 2, what do you get?
2.
Right? 0 plus 2 is 2. When I equals 3, what do you get?
0.
Plus 2 is 2. When I is 4,
You get 2.
plus 2 is 4. When I is 5,
You get 0.
plus 4 is 4. When I is 6,
You get 2.
plus 2 is 6. Right?
How'd you know to stop at 4?
What do you mean? Stop at 4.
Oh, you just went 1, 2, 3, 4, 5 to 6.
Yes, because I goes from 1
2.
to 6.
Okay.
Right, so you just sum up those terms.
Okay.
Ah, sum of squareds. There's actually a formula for this. And I don't remember what it is off the top of my head. We studied it in Calc 1 when we did Riemann sums. I don't remember what the formula was, though.
So it's just the numbers 1 to 10 squared added together.
Yeah, it's the sum of the squares. In this case, sum of the first 10 squares. Oh my God, I can't remember what it is now. N times n plus 1 times 2n plus 1 all over 6.
Should all add up to 85.
This looks like it's stat. There it is. Ha! I did remember it. N times n plus 1 times 2n plus 1 all over 6. So for this sum, it would be 10 times 11 times 21 all over 6. $385. Let's do this just to verify. $385. That's a lot easier than doing 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus meh. Remembering that formula is very handy. Compute the first 4 partial sums. So remember what partial sum is. You go from, in this case, 1 to big N. That's the nth partial sum. First partial sum, you just go 1 to 1. What's 11 minus 3?
8.
So the first partial sum is just 8. Second partial sum, you'd go 1 to 2. Well, we already have the first partial sum, right? The second partial sum would be the first partial sum plus the next term. So what is 11 minus 6?
5.
Now add 8.
13.
That'd be your second partial sum.
And then the next one's 13 plus whatever.
Whatever the third term happens to be.
When you plug in.
So 11 minus 9,
Is 2.
add that to 13.
Yeah, 15.
So now it's 11 minus 12.
1 plus 15 is 16.
11 minus 12.
Oops, negative 1. That actually 14, yeah.
Okay, so this is also going to require pattern recognition. So 1 plus 5 plus 9 plus blah, 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 plus 141. So what would the pattern be?
Is it n plus 4?
1 plus 4n, n equals 0.
1 plus 4n, n equals 0. Goes up to what?
Well, 40 over 4. 30.
35?
Sum. So that would give us 2556. Let's see. Oh my God. Really? This one's a joke. Should just be -1, 0, -1, 0. Because this is the sum of -1 to the n. Okay, then it looks like, yep, converging, diverging. Do I have time? Well, at least they tell you it's telescoping. That's nice. So what they want us to do is we're gonna do the same thing as we did. I erased it on that one telescoping problem. What was it, second to last? Find the nth partial sum, take its limit. So let's do a part 1 over n squared minus n, was it? N squared plus n. So it's 1 over n minus 1 over n plus 1. So the nth partial sum, and it starts at 6. Right, n equals 6 to infinity was the sum. And what does that limit? So what does that converge to?
Um, 1/6.
So the series converges, should be a sixth. All right, so you can work on assignment 17. You have 2 other assignments that went up. Second group assignment, that is the one where you're going to prove that the ratio of the Fibonacci numbers converges to the golden ratio. And then an article reaction. There's an article posted. So just read it, respond to the prompts. It's not a long article, definitely not as long as Lockhart's limit. I think it's only 6 pages, maybe less. Have a good weekend.